Hello friends. So today I would like to take an example of gravity, and from there we will try to understand the relation between kinetic energy, work, power and all that. So let's take a very simple case. This is your ground level and a ball is being just held at this position. This height is h. So if we just drop the ball, what happens? It will come down. Why? Because there is a force of gravity. If the force of gravity pulls it, it comes down. So what if I find that there is a displacement along this direction, downwards. The force is acting in the same direction. So what we are saying, that work done is your F dot dr. So it will be simply mg into h, because in the same direction, so it will just come out mg and integration of dr, that will be mgh. Now from work energy theorem, the initial kinetic energy was what? 0. Object was at rest. So what should be the kinetic energy final? That will be what? That will be just delta kinetic energy. That will be just work done, mgh. Very simple to understand. So it means when the ball is just about to hit the ground, it has a kinetic energy mgh. So if it has a kinetic energy, it could be equated simply by half m v square. And we can very easily find out what is the velocity at this ground level. So if we solve it simply, we find velocity to be root under 2gh. Now, I would like all of you to go in flashback in the chapter of kinematics and just try to solve this problem where a ball was just dropped from any height h and you were supposed to calculate the final velocity when the ball is about to hit the ground and whether you find that velocity to be same root 2gh or not. Or together we can do it. So we apply a very simple relation, v square equals to u square plus 2as, that is 0. So it will be just 2g, because there is acceleration downward, and s is your displacement h. It means v is root under 2gh. So the relation of kinetic energy as half mv square satisfies our basic kinematics. It means you can assume that yeah, we are going on the right track. So again, what are the different things happening here, which is actually emerging to be as a common single point? A ball is just being dropped, force of gravitation acts, it increases its kinetic energy, it increases its velocity, or apparently it applies force on it, it does work, and everything value we have already calculated. So we have found that this work is positive work because the direction of displacement, direction of force, both downward, same direction. So angle something between 0 to 90, if it is a positive work. Now let's make some slight bit of change. The same ball, but at the ground level initially, and it is thrown up with a velocity v, and it reaches a height h. The maximum height it reaches is h. Here the velocity becomes 0. So again, what's happening? As soon as the ball starts going up, the force of gravity starts to pull it down. So the direction of velocity, direction of force opposite, it means it's a retardation. So this retardation produces negative acceleration, and that is actually decreasing down the velocity. Now if I ask you tell me about the work done from the path position A to position B. Work done by definition is what? F dot dr. Integration sign we can take out because F is constant, that is mg. But wait a minute. This is dot. Displacement upwards, force downwards. Though the object's velocity is decreasing at every instant of time, but yet its displacement is positive y. Force is negative y. Angle between these two 180 degree. It means it should be minus mg h. So you can see the work done is minus mg h. So delta k E, that is equal to the work done. Actually, there is no point of writing this delta here. We can simply remove the delta. It is just work done. So it means it should be equal to minus mgh. So what do you mean by negative value of change in kinetic energy? It can be written as k2 minus k1. Now we know that final velocity is 0. It means k2 is 0. So minus mgh is equal to minus of k1. That is k1 is equal to mgh. So it means that the initial point when velocity v was given to this ball, it has attained a kinetic energy of mgh at that particular point. Afterwards, continuously its kinetic energy was decreasing because a negative work was being acted on the ball. So initial kinetic energy mgh finally turned on to 0 by the virtue of a work done in which the force direction and the displacement's direction was simply 180 degree apart. Now, what happens to the kinetic energy then? I mean, where does it go? Does it simply escape in the universe? Or what happens? Initially, a body is carrying some kinetic energy, a work is being applied on it, and we found that kinetic energy is being reduced down to 0. Till then, it's fine. Okay, good. So initially, it has energy. The form of energy was kinetic energy because it was by the virtue of motion. But basically, it has energy. And at this point, we are saying kinetic energy is 0. So how did it happen? Because in our class 8, 9 somewhere we must have studied law of conservation of energy. So where did this energy escape? Can you find it out? What role this work is being played here? What role does this work have? What is it actually doing? It is just reducing the kinetic energy. But by reducing the kinetic energy, what is exactly happening? It is transforming kinetic energy into some another kind of energy. Because we are applying a force, though it's reducing its velocity, but there is a field here, gravitational force. So this is the main cause of the force. So what role does it play? It is converting your kinetic energy into another form of energy, and that we call as potential energy. Now, right now we can see here that this potential energy is by the virtue of position. Its simple value is what? Initially the energy was mgh, kinetic energy was mgh, and final kinetic energy is what? 0. It means the change in kinetic energy is mgh. And we know, like by the law of conservation of energy, that energy is neither created nor destroyed. So it means simply this energy got transformed into potential energy. So that is the definition of potential energy, mgh. And this h is being taken from the reference level. So this is the new form of energy we are finding as potential energy equals to mgh. So if we talk it in a different way, that if a body is being set from ground level to higher level, there is change in its height, and that change brings in the change in potential energy, that is mgh. Suppose if I say it this way, that instead of a velocity, there is action of some force, some random force F, and this force is actually taking it to the topmost object. So first of all, to carry it above, this force should be greater than mg. So to reach to this point P, what's going to happen? What is the net force acting on the object? The net force is F minus mg, because mg's direction is downward, F's direction is upward. So we can write F minus mg into displacement h, and that is equal to your work done. So by the definition of potential energy, what was the potential energy here? Potential energy here was 0. And what is the potential energy here? Potential energy here is mgh. Now even at this point, the kinetic energy is there because the force is continuously acting on it. So what is the kinetic energy? Initially the work done was, there was no work here, 0. So the work done is F minus mgh, and that should be equal to your kinetic energy at this point 2. 1, 2. And initial kinetic energy K1 was simply 0. Initially the object was at rest. So this is the kinetic energy. So here you can see that the object is gaining kinetic energy as well as the object is gaining potential energy. In the previous case we found that energy was converting from kinetic to potential. But here both kinetic is also coming, potential is also coming. So who is bringing these many changes? It is all due to virtue of force. In earlier case there was only gravity, in this case there is force, capital force F. So it's bringing all the changes here. So before dropping down to some standard results, the theorem is actually valid all the time. I was just trying to bring down everything back to force, that all these relations, these are basically because of the virtue of force. The force plays the main role. And then we will understand right now the main definition of potential energy, and finally we will enter into the list of problems. So I hope this example must have got clear. Now let me again ask you, what is potential energy? Right now we just saw potential energy as mgh. But I can guarantee you that if you say to any person, and if you insist that what is potential energy, if he asks and you say it's mgh, he is not going to be satisfied, because this is not potential energy. This is potential energy only because of the virtue of position. The very simple way to understand potential energy is that at this point of time, when you are watching this video, you must be sitting at your table, on your chair, on your bed, and you must be in the most comfortable position you can at this point of time. You all must be. None of you must be trying to hide himself under the table or trying to chain him under a heavy load or try to get upside down or something like that. So why all of you, irrespective of whoever he or she is, all of you must be in the most comfortable position you can. Why? Because that is the state of least potential energy. So potential energy basically tells about the state of comfort in a layman's language. I give you another example. Suppose you commit any mistake in a school and your class monitor tries to take you to the principal, and the principal is a very damn strict guy. He's very strict. So what will you try? You will try to oppose your friend, your class monitor. You won't intend to go. Rather, you will apply a negative force. He will try to drag you to the principal. You will apply a negative force. You will try to get away from the principal. So why is it happening? It's happening because the principal himself creates a field of strictness around him. Now coming down to charges. What happens? Like charges repel each other, opposite charges attract each other. Why? In atoms, if you just excite the electrons go into the higher level and then they again emits electromagnetic radiation, and they try to come back down to the ground level. So why all these phenomena of nature happening? The only main reason is potential energy. Least potential energy maximum stability or comfort. So this is the reason. Everything tries to attain the most stable state. You are at your most comfortable state. The electrons want to be in the most stable state in the atom. The charges want to distribute themselves in such a manner that the entire potential energy of the system of charges drop down to the minimum value. The electron in hydrogen atom tries to stay in the ground level because the potential energy there is minus 13.6 electron volt, that is the least potential energy possible. The planets move in a circular path rather in an elliptical path in such a way so that the gravitational potential energy could be reduced down to the minimum value, possible value, attaining the stability. So all the physical phenomena which happen around you in the universe, if you just try to find out the reason behind this, then we will see a force that is trying to pull everything in the fashion in which they are, and the main purpose of the force is to let them attain the maximum stability. And the maximum stability comes only when the object is at least potential energy state. Now this potential energy can be because of different kinds of forces. Gravitational forces that lead to gravitational potential energy, which you just saw, mgh. This is your gravitational potential energy. Then electrostatic potential energy, that is denoted by K, Q1, Q2 by R. This is a constant. Then the potential energy burst precisely, which we have to study in this chapter, that is because of a spring. A spring we all are familiar with. What happens? If you try to pull it apart, you need to apply some force. Suppose this is the natural length of a spring. You just try to pull it by x unit. you need to apply some force F. If you further find to pull it a delta x unit, you need to apply a force F dash, and you will see that this F dash is significantly greater than F. The furthermore you need to pull this chain out, you need to apply huge amount of forces, and the amount of force actually increases every step. Why is it happening? If you just leave the spring at this point, what will happen? Eventually it will try to get down to the null position. Not in one step, maybe in after 2-3 steps. That will come later. What I'm trying to say is that this spring will always try to attain its natural length, because that is the most stable, most comfortable position for this spring. And for this natural length, there is no potential energy. Zero. So potential energy comes only when either you pull this chain out or you try to compress this chain. So if we try to understand it in a stepwise manner, this is the natural length L, and there is a block being attached to this. Block consists of mass M. Now what basic things need to be taken care of is that this spring is almost massless, so no need to consider its energy and all. Basically the kinetic energy will not come of the spring, rather the kinetic energy of the box, this block, will be considered. You apply a force F on this mass. What will happen? You will experience this. There will be a elongation delta x in the mass M. You applied a force, you try to pull it away, it got pulled. But believe me, if you further want to pull it beyond this point, you need to apply more force. Why? Because initially the molecular lengths, suppose was this between two molecules, that has increased to this. So the molecular separation at a molecular level, this separation, which should be like this, has reduced to this distance. So these molecules want to regain their shape, their original size. So how will they try to regain? It means they will have a tendency to oppose the external force, and that's why we call this as a restoring force. This is a restoring force. So this force allows any object under external force to regain its shape. So this is a tendency of anything. We have seen the same thing in a string as well. The string got elongated a little bit, so a string wants to attain its natural position. So that's why a tension is being created here. So here this force is called as restoring force. Now this restoring force, will it be constant or will it depend on something? So that you can find out experimentally very easily. You just try to pull it slightly, delta x, you need to apply force F. If you further want to go beyond this point, delta x dash, you need to apply F dash. If you further want to go beyond this point, delta x double dash, you need to apply force F double dash. And you will see that this F double dash is really greater than F dash, and that is greater than F. It's not constant force. As soon as the elongation is increasing, simultaneously the force you need to apply, that is increasing. So why we need to apply a higher force? We need to apply a higher force only when the restoring force is changing. Rather, I can say it's increasing, and that is increasing proportionally to the displacement. So we can write the restoring force F as minus of K del X. Now it won't be difficult to understand why I've put this minus sign here. You can see very easily that the displacement direction is this. It means the restoring force direction will be this. The restoring force will act always against to the external stimuli. The chain is being pulled away, so it will try to come back to the natural position, so it will try to come back to this point. Or rather, I should put this arrow. Now, suppose this spring, had it been compressed to this length, delta x. Here the displacement is along this direction. It means the restoring force will act this direction. The restoring force will push away the block to reach this natural position. So ultimately, the restoring force will always act to let the spring reach the natural position. So for that, eventually it has to be always opposite to the displacement of the point of object. So that's why it comes negative. F is equal to minus of K del X. So if this del X changes, it means, or the F will be changing. But you can simply put X, where X is change in length or natural length. Of a spring. F equals minus Kx. So this is the restoring force. And this restoring force is actually creating potential energy. And the term we use this for this potential in the spring is the elastic potential energy. So again, in this point we got a force. In this case, the force was gravity, mgh. In this case, the force is the restoring force of the spring. So now, we will deal it mathematically. Natural length of the spring. Now the spring being pulled by distance x. Consider this to be a small distance. So what are the things to be calculated? Can we ask that what is the work done in taking this object from this position to this position? By definition, it should be simply F dot x. The force being applied is in the same direction, so no meaning of dot, we can simply replace it by x. And if its force is constant, it's simply Fx. So what this work is bringing? This work, it means there should be kinetic energy. So initially, what was the kinetic energy? The object was when at rest, so 0. But at this point, what will the kinetic energy? Kinetic energy will be simply Fx. Will it be or will it not be? Is there a mistake here? There is a mistake here, which I made out to make you remember always this point, that whenever you are applying this force F on an object, quickly there is a restoring force always, if we are taking it as a small f. So as soon as this F does a work positive, because this direction of F and displacement same, this F restoring force is doing a work negative. So right now we will assume that this F is almost equal to small f. So if we follow this condition, then what will happen? This block will move, but move very slowly, because there will be hardly any acceleration, because acceleration is your capital F minus small f by m. So if this value is very small, there would be hardly any acceleration. So if there is hardly any acceleration, there would be hardly any velocity. So your velocity is almost zero. So we are assuming here that we are just displacing the object, but we are displacing it very slowly. As a result of that, there will not be any kinetic energy. Rather, the kinetic energy will be also almost zero. So did it clash with your work energy theorem? It actually did not. Why? Because this was the work done only by the force F. What about the work done by the force small f? That will give you minus of Fx, because its direction is this, displacement is in this direction. If you add W1 plus W2, you get capital F minus S into x, and that is almost equal to 0. So up to this point, no change in kinetic energy and no work done, both 0. But then what changed? Because the picture seems as if something must have changed. Then what is that? The thing which has changed is your elastic potential energy. And why? Because of this restoring force F. Because at this point of time, all the molecules inside the string, they are unstable. They have been elongated. They are not at their natural position. So that's why they possess some energy, because their stability position has been deflected. So the stability has gone down. It means the energy, and that energy we call as elastic potential energy, it has gone up. Because maximum stability, minimum energy. Stability goes down, energy goes up. This is what? Potential energy. So the potential energy comes into picture. And what is that? The potential energy is basically negative of the work done. By internal force. Here, internal force is your small f. So that did a work negative. So it means this term is a negative. You apply negative sign all below that, before that, you get a positive quantity.